we are looking for the differential area element. In any coordinate system, we had better to express the vector in terms of Cartesian coordinate that we are very familiar with. Cartesian coordinates, E1, X1, E2, X2. If I want to make use of polar coordinates in 2 dimensions, X1 is R cosine, and X2, that is Y, it is a R sine theta. Okay. If I want to find the differential element along the direction of radius, for example, from R to R plus dr, R plus dr, and keeping the theta constant. That means we need to take the partial derivative with respect to r. And if I want to find the displacement along the direction of theta, then we change the theta to theta plus d theta and keep the radius the same. But before we study these complicated cases, we first consider simplest case, that is the differential element in the Cartesian basis. If I want to change, let me just simplify this one into x and y. The differential displacement element by changing x only is just E1 dx. How can I find this? It is just take the partial derivative of the position vector and multiply the differential of that variable. This is this. And if I want to find the displacement along the y-axis, then I take the partial derivative with respect to y of the position vector and multiply dy. That is just this. What is the area element spanned by this displacement along the x-axis and y-axis? That is E1 hat dx, that is E2 hat dx. What is the area? This area can be obtained by taking the cross product, and this cross product is always perpendicular to the xy plane, so I multiply the unit vector along the z-axis. Then the final result is just simply dx dy. That is the area on the xy plane with the region x from x to x plus dx and direct product of y comma y plus dy. Here the direct product means the combination of a comma b in the range. This in the range, this. Okay. Now let us extend this idea to the polar coordinates. Polar coordinates, I use this definition. X coordinate is r cosine, y coordinate is r sine. Now, I would like to vary r only, that is to take the derivative with respect to r. If I take the derivative, then what I get is this E1 hat cosine plus E2 hat sine, right? That is the unit radial vector. And this is this. So I have to multiply the differential of r, dr. So dr is multiplied. What happens to the case when I vary theta from theta to theta plus the d theta? Then again, I take the derivative with respect to theta. If I take the derivative with respect to theta, what I get is minus here, round theta, round x over round theta is minus E1 hat r sine theta, and this one E2 hat sine becomes cosine, so r cosine. This is the partial derivative of the position vector with respect to the angle theta. Now I need to multiply d theta. Finally, what I get is this form, and we have the additional factor that is r. This is arc length. We have a radius, keep the radius the same, but angle from theta to theta plus the d theta. Then what is the arc length? That is r d theta. Is r d theta. And what is this unit vector? This unit vector is along the tangent direction, that is perpendicular to the radial direction. So if I want to express the area in terms of these two-dimensional polar coordinates, what I want to do is this is dx radial direction, and then we have dx tangent direction. We have this area. This area is the same as this one. I translate this d theta, dx theta into here. Then we have a right angle. Always radial and tangent direction. They are always perpendicular to each other. This is dxr and dx theta. We take the cross product, and they are always on the same plane, xy plane, and this cross product is always perpendicular to this xy plane that is parallel to E3 hat. So in a similar manner as we have done with Cartesian coordinates, what we find is finally, after all the detailed calculation, what we find is simply this. This is dr, this length along the radial direction. We have r from dr, and tangent direction, we have r, and angle is d theta, so arc length is r d theta, and they make the right angle. So this rectangle, actually it is a curved area. However, in the limit, dr goes to 0 and d theta goes to 0, it becomes an exact rectangle in the limit, in these limits. And this is dr, and this is r d theta. Therefore, the area is r dr d theta. Okay? This area can be expressed as these two. What is that? This is the same as this triple scalar product. Triple scalar product is what is that? It can always be expressed as the determinant of three vectors. The E3 hat is here, and is this, and this is a dxr. I have pulled this r out. So if you compute this determinant, it is just like the partial derivative of x and y with respect to r and theta. Finally, because it is a two-dimensional case, it's x, y, and r and theta appears in the first column. We have x, second column we have y's, the first row we have r's, second row we have r thetas. This is called the Jacobian. Then, however, even though we do not know the details about computation of this Jacobian, what we know is directly from this triple scalar product definition of area. Very simple. And this is another way of writing this triple scalar product. And this is called the Jacobian. Without considering the Jacobian, that is in here, this is Jacobian R. Without considering this Jacobian, we have a wrong result. For example, we have a function of x and y integrate over some region on the xy plane, this integral. And this is a function of x and y only. However, sometimes it is convenient to compute this integral. For example, if I have a circle, this integral is much convenient if I make use of r and theta. But it is rather cumbersome to compute the integral over x and y. In that case, the reason is that r theta, r is 0 to r, 0 to some radius r, and theta is just simply 0 to 2 pi. Simple. However, if I do want to compute this xy integral, I need to divide this one as a complicated one. For example, I need to cut it in this way, and this is the x-axis, and x ranges from minus r to r, minus r to r, and y ranges from here. For example, if I have some x, because this is r, and this is x, and this is y, y is the square root of r squared minus x squared. Here, this is a minus, and this is a plus. So, if I erase everything, if I want to carry out this integral, I need to evaluate this integral as from dx running from minus r to r, and dy runs from minus r, square root r squared minus x squared plus this kind of integral should be done, f of xy. Sometimes it is very complicated. However, I can always express in terms of this integral as a very simple integral. However, even though these ranges are very simple, if I miss this Jacobian, then my result will be wrong. So here I substitute x is r cosine and y is r sine. I need to multiply this r. R may be computed by using this determinant that is called the Jacobian, but that is simply coming from this triple scalar product. I told you this triple scalar product represents the volume of a simple cube, and this is a fictitious cube who has the unit height along the z-axis. So that is called the Jacobian. Okay, and this is a simple case for the two-dimensional polar coordinates. And in three dimensions, we introduce a cone. There is a cone at xy and z-axis. And if I have a radius, then I introduce the angle that is called the polar angle. Polar angle theta is always measured from the z-axis to the radial direction. In that case, what is the z? That z is, because this is right angle, radius times cosine theta. This is r cosine theta. And we have a planar radius that is on the xy plane, and we find that this is a right angle. We have a radius r, right angle, and this is theta. This is a half a pi minus theta, so this is r sine theta. So planar radius that is on the xy plane has the radius r sine theta, and it ranges from this x-axis and return to the same position. Remember, this polar angle theta runs from 0 to minus c-axis, that is theta equals pi. However, we have azimuthal angle that ranges from 0 to 2 pi. So this phi, this is a planar radius, this is planar radius r sine, and r sine is the z component, this is r sine, and we have azimuthal angle dependence phi. So theta runs from, if I want to evaluate the theta integral, 0 to pi, and we need to find 0 to 2 pi. But as you know, this is angle. Angle does not carry any dimension. We need to multiply the scaling factor to make this one to have a length dimension. That missing factor can be included to find out the Jacobian that makes this one complete area or volume. We write down the position vector x(e1 hat, y(e2 hat), and z(e3 hat), and substitute these values into x, y, and z. And we take the partial derivative with respect to x, y, z, then simply we have this kind of displacement along the x, y, z direction. But it is not the end of the game. We would like to study the variation along the radial and polar angle and azimuthal angle dependence. In that case, I take the derivative with respect to r, theta. Oh, it is missing. This should be phi. And you will find radial direction is just the dr. And in here, we have angle theta and radius. And if I vary this angle theta, this arc length is r d theta. And in here, we have a planar radius on the xy plane. Planar radius on the xy plane, theta. This is xy plane. This is r sine theta. This is the radius, and then azimuthal angle rotates on the xy plane. So that's the reason why we have r sine theta multiplied by the differential of azimuthal angle. And if you carry out this partial derivative with respect to r, theta, and phi for these explicit x, y, and z components, you will find these vectors. And in here, this is nothing but the unit vector along the radial direction, and this is nothing but the unit vector along the theta direction. However, we have additional factor r because this is the angle, and only if we multiply the radius and angle difference, we have arc length, right? In a similar manner, when we vary the azimuthal angle, the same thing appears. It is proportional to the unit vector along the azimuthal direction. However, this is angle only. I need to have a scaling factor that is a radius. That planar radius on the xy plane is just simply r sine theta. That's the reason why I have this. There is no factor. There's a factor of r sine theta appears. As a result, for example, if I compute the volume in the three-dimensional space, dx, dy, dz is the volume element in the Cartesian coordinates. But if I make use of this spherical polar coordinates, the volume element will be the triple scalar product of these unit vectors that are all orthogonal to each other. Therefore, what I have is dr, r d theta, r sine theta, d theta, sine theta, d phi. This product, that means what is that? R squared dr and sine theta d theta, and then d phi. This product makes a volume generated by the differential of dr, d theta, and d phi. Please remember, r is a variable of length, that there is no scaling factor. Theta is an angle, so to produce the volume, the length, I need a radius. And d phi is an angle on the xy plane, and its radius is r sine theta. So this is radius to make a volume in the three-dimensional space using polar coordinates. I need to multiply these scaling factors. That's quite important. Again, we can do the same job to compute this triple scalar product, but we know the answer already. This is a little bit complicated mathematics, but we know the answer. What is the answer? We know the structure, but we don't have to compute this because we know the answer. This is the answer. So Jacobian in here is r squared sine theta, sine theta. However, this is the volume. In here we have dr, d theta, d phi is missing in this problem, right? Finally, this is just the details of the computing the determinant, but it looks complicated. However, we know the answer. It should be in this form. Finally, at the end of the day, we hear dz is missing. dz is missing. But page 7. Page 7. Until dx, dy, dz. Missing. Okay, if I want to replace this Cartesian coordinate integral in the polar coordinate integral, everything is fine. We need to multiply the Jacobian to reproduce the volume. This is the volume. This is not a volume. We need a radius. We need a radius. We need a radius for theta, that is r. We need a radius for phi, that is r sine theta. So we have r squared in here, and we have sine theta in here, and we have d theta. So we know sine theta d theta equals minus d cosine theta. But we know 0 to pi d theta sine theta can be replaced with 0. At 0, cosine is 1. Cosine pi is minus 1. Minus d cosine theta. This minus sign flips the upper limit and lower limit. That's the reason why I usually write any angular integral in polar coordinates. I do not evaluate the theta integral. I do evaluate the cosine theta integral. It is trivial. Much simpler if I replace this one in this form. Anyway, the three-dimensional volume in the three-dimensional polar coordinate system is always represented by this, and you will find that this r squared sine theta is the Jacobian of from the Cartesian coordinate system to the polar coordinate system. We have this integral. This is called the Gaussian integral. Gaussian integral appears, for example, you have normal distribution in the statistics. This comes from this exponential minus x squared distribution. It is well known, and it is equal to square root of pi, a very strange integral. But let me show you how to evaluate this one by making use of this kind of method we have mastered already. Why don't we multiply this integral twice with a different variable, independent variable? However, we can multiply these integrals all together, and revise this square of integral into a multiple integral in 2 dimensions. XY plane can be expanded using x and y variable from -infinity to infinity and -infinity to infinity for y variable. However, I can rewrite this one into polar coordinates. In polar coordinates, the radius r runs from 0 to infinity, and this polar angle is 2 pi. So we have 5. Actually, this is azimuthal angle, so runs from 0 to 2 pi. And I know this integral dx dy, this can always express as integral dr d theta, and this is the we need the scaling factor to make this as a length element. There's arc length r d theta, so this is the Jacobian. So if I rewrite this one, this 2-dimensional integral in terms of the Cartesian coordinates can be expressed as a polar coordinates integral, including this Jacobian. Then everything becomes very simple. The dr integral and Jacobian is r, and we have x squared plus y squared equals r squared. So we have this integral as e to the minus r squared. And this is a trivial integral, you know, this is 2 pi. And what is it? This one can be converted into a simpler integral by replacing r squared with t. Then if I take the derivative, it becomes the 2r dr and dt. So therefore, r dr, we have r dr. r dr is 1/2 dt. Therefore, this integral looks complicated. However, it becomes a trivial integral. We know this is just 1. Therefore, it is 1/2. This radial integral is 1/2, and this angular integral is 2 pi. 2 pi multiplied by 1/2. Everybody knows that it is pi. If square is pi, and I can be plus minus square root of pi. However, I know, this is a positive number. Any exponential something with a negative sign, it is a positive definite. It can never, exponential can never be 0. It is impossible to have negative value. And positive integrand integrated over the whole region, it is a positive definite. Therefore, I have the final result. This Gaussian integral is the square root of a pi. Now you become very clever to extend this idea to find out what happens to the n-dimensional Euclidean space. Anyway, before we do that, let us consider this solid angle. Solid angle is nothing but this. You are familiar with this. What is that? This is the angular integral that appears in the 3-dimensional polar coordinates. We have dx, dy, and dz in 3 dimensions in Cartesian coordinate can always expressed in terms of r squared, the dr, r squared, d theta, sine theta, d phi. The reason is that d theta needs a scaling factor that is a radius. D phi needs a scaling factor that is a planar radius. That's the reason why we have r squared, and sine theta here. And I told you this integral can always express in terms of -1 to 1 d cosine theta. And this is a trivial integral from 0 to 2 pi. And we have radial integral. Any 3-dimensional integral in terms of polar coordinates is factorized into the radial integral and angular integral. And this angular integral is called the solid angle. And you will find the solid angle is 4 pi. Why? This is 2. This is sine theta d theta is d cosine theta from -1 to 2. Trivial integral is 2. And this is a trivial integral, so 2 pi. 2 pi times 2 is 4 pi. 4 pi is the solid angle in the three-dimensional space. Now, what we'd like to extend this idea is to increase the dimension from the 3-dimension to n dimension. Perhaps you are not familiar with this. However, we have to know this because before the end of this semester, we have to study Maxwell-Boltzmann distribution. This integral appears indeed. The usual textbook, they do not carry out the integration and they just discuss qualitatively. But what I want to do is let you do this integral. This is actually very trivial once you know how to evaluate. So now you are ready to do that. You know how to find out the total differential, and using total differential, you can evaluate and very complicated. It looks very complicated, but in many cases you can do the integration by parts, for example. Let me introduce a very strange integral. You have a very simple integral. This integral is just 1. It is familiar with this, but we have additional factor of powers of t. And at the end of the day, you will find that this is nothing but the factorial. In case you substitute integer, that is positive integer. Anyway, we can change the variable to find that, first of all, this trivial integral shows that if I substitute alpha equals 1, this t power disappears and it becomes a trivial integral that is 1. And actually this is called 0 factorial. You will find that. And then this is just we already have learned how to differentiate the product function, but Leibniz told us. However, in this case, this integral is from 0 to infinity. You will find that this one vanishes, goes to 0 as t goes to 0. And this factor goes to 0 as t goes to infinity. Okay? So you will find that this is a mathematical induction. If you know the answer for this, you substitute the value for alpha plus 1, just add by 1, and find out the result is very similar to the previous one, but you will find we have additional factor alpha. It is a straightforward calculation by making use of this expansion and integration by parts. Anyway, n factorial multiplied by n plus 1. What is that? That is called n plus 1 factorial. Something like that. So you will find this one has a very similar structure as the factorial. The only difference is that there is a shift by 1 in variable, the argument. Anyway, we go further by replacing this alpha that is not an integer. For an integer, you do not have to make use of this complicated integral representation of this gamma function. However, in case you have non-integer as an argument, let us substitute 1/2. Alpha minus 1. Alpha is 1/2. And now, why don't we change variable? T equals x squared. Then it becomes dt equals 2x dx, something like that. So we substitute in here. 2x dx appears in here, and we have this one to be expressed as t is x squared, and 1/2 minus 1 is minus 1/2, and this one is 1 over x, and this one became this, and x cancels, And what you end up with is 2 times, this 2 times 0 to infinity minus x e to the minus x squared dx. Oh, you're very familiar with this. This 0 to infinity. However, we have a factor of 2, and this is an even function in the negative region 2. So I can absorb this factor of 2 by extending the lower limit to the minus infinity. You know the answer. This is, what is that? This is Gaussian integral square root of pi. Aha, you know gamma function with the argument 1/2 is the square root of pi. Everything is done. Using this fact, we can extend this one multiplying the n powers of n of a Gaussian integral. If you integrate this, you will face that this integral over the Cartesian coordinates, they are not xyz, but x1 to xn. That's a n-dimensional Euclidean space and n-dimensional Cartesian coordinates. However, in the n-dimensional Cartesian coordinates, we can always use the similar method to describe the polar coordinates. The sum of the Cartesian coordinates squared should be replaced with the radius in the n-dimensional Euclidean space. And I don't know right now how to evaluate the solid angle in n-dimensional Euclidean space. However, let's assume that we have integrated over the whole angular integral. Then the only remaining piece is the radial integral. Fortunately, the whole value is already known because it is a product of powers of this Gaussian integral. And every single Gaussian integral is a square root of pi. And I know the answer, that is n over 2 of pi. Therefore, if I substitute everything all together, and we have only a single integral remaining in here, and this is, by changing variable, you will find that this ends up with the gamma function. Gamma function is closely related to the factorial function. Finally, this is the whole integral that is called the pi, this. And Jn is the radial integral. I substitute this result in here, and this is solid angle in n dimension. And actually, we can substitute values, n equals 1, 2, 3. Substitute this master form. This is valid for any case, 1, 2, 3, 4 to infinity. And you are very familiar with the 4 pi, that is the solid angle in 3 dimension. And this is the solid angle in what? 2 dimension. 2 pi r is the circumference of the circle. 4 pi r squared, that is the surface of the 3-dimensional sphere. Okay, now we understand the surface of n-dimensional Euclidean space is always expressed as radius to the n-1 power, and the coefficient is the solid angle. Okay, so 1-dimensional, 2-dimensional, and 3-dimensional. Perhaps you can see I did this kind of higher order piece that do not appear in the exam. However, as far as these dimensions are concerned, now you can explicitly evaluate these formulas for the surface and the volume. And volume is just integration of this radial integral from 0 to r. Then this integral will appear r to the n-1 dr, 0 to capital R. That is 1 over r and something like that. So volume of the n-dimensional sphere in the n-dimensional Euclidean space is the solid angle divided by n and radius to the rth power. And you are well familiar with, you memorized this long time ago, but now you have mastered how to evaluate all these things. So now it is trivial to you. Finally, we have it looks at first look, it looks very complicated. However, this is a main part of this class. We have a triangle. You learn triangle from the elementary school, and now you know how to evaluate the area of a triangle by making use of the cross product. Let me call Q a point inside the triangle, and from Q to vertex A, B, C are vertices. Vertex, and they are vertices. From any point Q inside the triangle to each vertex, I attach a star. A star, B star, C star, something like that. Now, cross product will give you the area of a parallelogram, and what happens to the area of a triangle spanned by these two vectors. This area is 1/2 of A cross B, something like that. So suppose that I have A star and B star, then area of this triangle is A star cross the B star. Because it is a vector, and this vector is perpendicular to this plane, I just multiply the unit vector along the z-axis, then this will be 1/2 of this will be the area of this small triangle. So A cross B is in here, this area. B cross C, this area. C cross A, this area. Understood? What is the area of the sum of these three triangles? That is the whole triangle. Okay, so that's the reason we have factor of 1/2 that is multiplied. Factor of 2 is multiplied to have this factor of 2 migrated on the right hand side. So sum of these small triangles is just the whole triangle. Jacobian, we learned Jacobian to transform a multidimensional integral from the Cartesian coordinate to any other coordinates, and Jacobi is very good at measuring the area, and this is a very famous formula coming from Jacobian. It looks complicated, but we'll know how to evaluate this triple cross product by applying back cap rule. Back cap. Using this formula, this is for the A cross B cross C, and substitute, you can make a cyclic permutation of this ABC in these three pieces, and you will find this one appears in here with negative sign, this one appears in here with negative sign, and they cancel exactly. So this is the exact zero, and that is called the Jacobian. Jacobian is the adjective of this mathematician Jacobi. He told us this is identically zero. And why don't we compute this one in here? What I do is multiply C cross, multiply A cross, multiply B cross. Okay, so C cross, A cross, B cross on the right hand side, and left hand side sum. You're familiar with this. What is that? Sum of these three expressions must be zero. This is a very trivial return. Looks complicated, but because of Jacobian identity, the sum is a zero. Sum is zero, that means the right hand side sum is also zero. And you will find this is nothing but the A star, B star, C star was defined to be the vector from a point inside the cube two vertices, this one, this one, this one, that means A star is A minus Q and B star is a B minus Q, something like that. So we substitute this one into these expressions, and you will find, what you'll find is these three, sum of these three, because A stars are replaced with these, and subtraction, they are common to every three term, and sum of these three is the coefficient of Q, and sum of these three is just sum of these three, that means the whole triangle. So this is the whole triangle. Finally, it is exactly 0. That means Q is the center, not the center, any point inside a triangle. And we have a total area of the triangle. Divide this one. Divide. So what we find is this area divided by the whole area, and this area divided by the whole area, and this area divided by the whole area. So the fraction of area of the subtriangle, they are called kappa A, kappa B, and kappa C. And actually these three sum is the whole area of the triangle. This sum of these three numbers is exactly 1. This number is called the barycentric coordinates. Barycentric coordinates. Do you know Möbius? Möbius band. Möbius is actually the physicist. He created this very strange variables. Sum of these three is equal to 1. Is a redundant, linearly dependent variable, but very convenient to describe the physics of a triangle. Okay. Finally, we arrive at the delta function. Delta function, you just memorize this. Delta function is always 0, except for a single point that is divergent. However, it gives a certain value. If I multiply any function, it produces the value of the function at 0. If I substitute f of x equals just to flat function, constant function, what I find is integral of delta is just 1. What's that? It is just like a very sharp peak at 0, but this area is 1, but the width goes to 0, the very sharp one. It is in physics, point particle, point mass, point charge, everything, this kind of thing can be expressed in terms of delta function. So though we consider a particle is does not exist in nature, but mathematically it is very convenient to employ mathematical formulas. So we use a particles concept. However, in many cases, if I consider particle derivative goes to infinity, and sometimes mathematical structure of this physical description becomes completely wrong. It looks like that. However, in fact, that has a consequence of employing particles concept. This Dirac introduce Dirac delta function that is not a function, instead of a kind of distribution, it is a very convenient for our physics analysis. And he is a Nobel laureate, and when Dirac introduced this idea, mathematicians did not accept this idea. However, now it is well known, and many people, including mathematicians, are using this concept frequently. Simply, we multiply some argument, some constant to the argument, and we can change the variable. We find that this Dirac delta function has the form ax, then 1 over absolute value of a is multiplied in here. The reason why we have absolute value is that the Dirac delta function is an even function. Left-right symmetry. It is a positive definite, and it is an even. Odd function is, this kind of thing is odd function. This opposite, the sign is different, but this is an even function. And if we change the variable, you will find delta x minus y multiplied by f of x integrated over x. Then you can choose the value at y. It is consistent with the fact that delta function integrated over minus infinity to infinity, this is f of 0. When these arguments are the same, it gives the value of f at 0. But if it is x minus y, something like that, then it gives the value of f at y. Anyway, this problem does not appear in the exam. If you are interested in, then you can find that this delta function is very nice to find out the change of variable. And today, the first part of this class, we have derived the Jacobian by changing the multidimensional integral into different coordinates. And here we have a rotational version of the change of variable. After the rotation from the coordinate xy to x prime y prime, the integral becomes this kind of form. And in here, Jacobian is exactly 1 because the Jacobian is cosine squared plus sine squared, that is 1. So if you like this problem, you can do that, but the exam, it does not appear, the number 10. Anyway, finally, I'd like to evaluate this integral. Area of a triangle is now expressed in terms of two-dimensional integral among the 3 barycentric coordinates, kappa, a, b, c. And I told you kappa a, kappa b, and kappa c is just a partial fraction of the whole triangle's area. And this area divided by the whole triangle's area, and this area divided by this area divided by this are called kappa A, B, and C. And because they are fractions, and the sum of the fractions must be 100%. And area of this triangle is now parameterized by this two-dimensional integral. And the reason why we have introduced the Dirac delta function is this. We can parameterize these two-dimensional integral by including the Dirac delta function into three-dimensional one. Because after we integrate over a variable that is included as an argument of the Dirac delta function, then what we have to do is just to substitute. For example, if I integrate over this, what I have to do is just to replace this one with argument this is 0 after this integral. That means kappa after this integral, kappa c is replaced with 1 minus kappa a minus kappa b. That means actually, if we rewrite this one, kappa a, kappa b, and kappa c equals 1. What is that? The area of sub-triangles is just the whole triangle's area, the simple one. Anyway, these various kinds of parameterization to find out the area is actually the same as expressed as the three-dimensional integral multiplied by the Dirac delta function. And that those integral, this integral, why don't we evaluate this integral? What I have to do for the three-dimensional, the KC integral, we have K kappa C is 1 minus kappa A minus kappa B, this replacement. However, there is no place to substitute it here. So it is nothing but this, except that B, kappa B integral is not over 0 to 1 because these sum kappa and kappa B and kappa C, some of the, for example, A plus B equals 1. A ranges from 0 to 1 and B ranges from 0 to 1 minus A because A plus B must be 1 and A is greater than 0, B is greater than 0. Why? Kappas are the partial fraction of the area and area must be positive. This area must be positive value. So if sum is 1, and each of them is a positive definite, for example, it is a 0 to 1, be 0 to 1, something like that. In this double integral, the range of A can be extended from 0 to 1, but range of B cannot be extended to 1, instead 1 minus A. So just like that. So now we carry out this two-dimensional integral. This integral is trivial. Just upper bound, upper limit is this. And it is something like 0 to 1 dx, 1 minus x. This integral is 1, and this integral is 1/2. So 1 minus 1/2 is 1/2. We can do the similar job for kappa A. Then what I have is do the same job, and we have a kappa A in here. And we have kappa A, 1 minus kappa A, exactly the same, but additional vector kappa A. What is this? dx, 1 minus x, 0 to 1. This integral, 0 to 1 integral, x minus x squared. That is, x integral is 1/2, x squared integral is 1/3. That is 1/6. Similar integral can be evaluated in a similar manner, and this one is integral 0 to 1 dx x squared minus x cubed, that is 1/3, and this is 1/4. So this is 1/12. Finally, if I have Ka, Kb style, then do the same job in here. Ka integral, Kb integral is replaced with 1/2 Kb squared, but upper bound, upper limit is this one. So, and then expand this one in this form, and Ka integral is finally done with over a factor is 1/2 minus 2/3 and 1/4, that is 1/24. Finally, let me compute the center of mass of a triangle, all by making use of all our results. I told you the area of a triangle can be expressed in terms of these barycentric coordinates, and if I rescale this one with mass by multiplying the surface mass density, that is a total mass of the triangle divided by the area of ABC cancels, and 2 times the mass multiplied by the differential product of the two barycentric coordinates. I told you this two-dimensional integral can always express in terms of Ka, kappa b, and kappa c multiplied by this one minus kappa a, kappa b, and kappa c. And center of mass is a differential of mass multiplied by the position vector. And I told you the position vector is simply kappa a vertex, kappa b vertex, kappa c vertex. Now, we have integral table. This single power integral, what was that? Single power integral. This three-dimensional integral with the kappa a, you can find the same result for kappa a, kappa b, and kappa c. Single power will give 1/6. Now I have obtained this integral is trivially all 1/6. All 1/6 is multiplied in here, and we have additional factor of over a factor of 2. 2 times 1/6 is 1/3. Every vertex position vector is multiplied by 1/3, and this is the center of mass of a triangle. It looks complicated, but what I have used is a trivial three-dimensional integral. It is a three-dimensional integral, but by making use of the Dirac delta function, it collapses to a two-dimensional integral. They are mostly trivial, just a combinatoric factor. And now we have, time is up. And this one is the combination of the two system of particles, and what happens, we see what happens to the center of mass of composite system, and I think it is well explained in the original version of X11. Okay, that's it for today.